All right, welcome to our 18th lecture of the semester here. So as I was saying right before I started recording, this is going to be the last lecture that's whose material is going to be on the upcoming exam. So remember, we have an exam this coming Friday, not today, but next Friday. And the agenda for next week will be on Monday. We'll be doing a lesson that will be on the next part of the class, which will be on integration. And then on Wednesday and Friday, what we're going to be doing is we're just going to be reviewing for the exam. So on Wednesday, I think I'm going to do what I did last time. And I'm going to just work my way through one of the old exams. And then on Friday, I'm just going to take general questions from you guys, kind of like last time. All right. Anyways, let's go ahead and get started here. So today we're going to talk about something called Lagrange multipliers. Now, what on earth are these? This is actually another way of optimizing functions, although this time the functions will be subject to a particular constraint. So for example, we might want to make this number as big as possible, provided that this function or this equation has to be true here. All right, so what does this mean? Well, let's take a look at the domain of our functions here. And let's say that f has these level curves. So maybe this is like f is 1, f is 2, f is 3, or something like that. And then here's g. So g is kind of meandering its way through here, and then goes this way or something. Who knows? This one's g. So what we're going to try to do is we're going to try to find when this curve g intersects the biggest level curve that we are going to have. So in this case, it looks like the biggest value of f that it touches is going to be right there. So that's effectively what we're trying to do with this optimization method. Okay, now notice in this picture that they seem to intersect where their tangent lines are the same. So I could draw the same tangent line for both of these guys. Now, it's not just a coincidence based on the picture that I drew. This will actually always be the case. So the curve f will intersect g at f's highest point when they're going to be tangent to one another. Now, why does that have to be true? That doesn't initially make any sense. Well, let's say that we weren't tangent, right? And let's say that g instead maybe went like this or something. Then what we could do is we could find an even bigger level curve. Maybe f is like 3.5 or something like that out here and go even further. So wherever it ends up, it has to just barely touch that point, because if it didn't, you could end up going further. Or maybe for minimization, you can end up getting a lower value in that case. So it seems that wherever we intersect our biggest point, we're going to be tangent to it. Now, why does this matter? Well, let's say that we looked at the gradient vectors for both of these functions, right? So the gradient vector, remember, that's perpendicular to the level curve. So the gradient of f might be something like this, but then the gradient of g will also have to be in the same direction because they have the same tangent line, meaning that perpendicular to them is in the same direction. So this means that the gradient of f needs to be parallel to the gradient of g. Okay, now when two vectors are parallel to one another, that means that one is a scalar multiple of the other, right? That's what it means when two vectors are going to be parallel. So that means that the gradient of f is going to be some constant, which is traditionally called lambda, times the gradient of g right here. And this is what we're going to be looking at in today's lesson. We're going to use the fact that the gradient of f needs to be a multiple of the gradient of g, and that's going to limit what our x and y values are going to end up being. So that's kind of the overall philosophy of what we're talking about today. What's the Greek symbol called? This is lambda. I'm not exactly sure why this is lambda. It may be lambda because that's L for Lagrange. I'm not sure about that one though. Okay, and the next theorem right here is essentially just summarizing what I just said. So suppose f and g have continuous first partial derivatives such that f has an extremum on the smooth constraint curve g. So remember, we need to be on this curve g. That was one of the main points of this. So if the gradient of g is non-zero, then there's a real number lambda such that the gradient of g is, or sorry, the gradient of f is a multiple of the gradient of G right here. All right, and then the scalar L is called the Lagrange multiplier. Okay, so, all right, that's a nice theorem and all, and I guess it kind of makes sense based on this picture, but how do we actually use this in reality to find our, to optimize things? Well, what we're going to do is the following. We're going to set up a system of equations for x, y, and lambda. And the system of equations is going to be this gradient equaling lambda times the gradient of G. Now remember, this is actually two equations in one, right? Because we're going to have partial f, partial x, partial f, partial y, equaling lambda, and then the G partials. So we technically get this equation, partial f, partial x is lambda, partial G, partial x, and we get this equation right here. So there's really two equations in one right here. And then we have the constraint that our G of xy always needs to be a particular constant value. So what we're going to do is once we solve the system of equations is we find a few points that work. So maybe there's multiple x and y values that satisfy all of those equations. Then what we do is we do what's similar, kind of similar to what we did last time. We make a little chart and then we see which one's the biggest and which one's the smallest. And that will give us our max and min. So this is kind of a different way of going about finding which points are candidates for your max and min. And then you compare them in exactly the same way that we did before. All right, so let's go ahead and do this. And it may actually be easier for us to do this on a problem that we've already done to kind of compare how this goes. So you may recognize this function from before. We're trying to find the maximum and minimum values of x squared minus y squared minus 1. The only difference is that this time we have x squared plus y squared equals 1. So last time we were looking for the maximum values inside a disk, but now we're just looking for things only on the unit circle. All right, so we don't care about what's going on in the middle of this. All right, so as always, we're going to have our Lagrange multiplier equation where the gradients are parallel to one another. And then we're also going to have our constraint equation, which is x squared plus y squared equals 1. All right. Are we restricting a domain to find an optimal solution? Usually this has some kind of physical meaning to it. Like, do you guys remember back in Calc 1, the optimization problems? Like, oh, you're a farmer that has 100 feet length of fence, and you need to build the biggest area, like, pen that you can. You may not remember that fondly because those problems tend to be the harder ones in Calc 1. But that's essentially what we're doing here. This is the saying, oh, we have 100 feet of fence, and then this is we want to make this as big or maybe as small as possible. That's kind of the analogy going on here. All right, so in order to do this, let's go ahead and find our gradients. So the gradient of f is 2x, and then it looks like we have negative 2y here. And then the gradient of g, and by the way, with both f and g, you need to make sure that everything's on the same side except for maybe a constant. So we don't need to do anything here, but if there were maybe like a 2x or something over there, we would need to move it to this side right here. All right, and so we're going to do the gradient here. We have 2x and 2y, like that. All right, so let's see here. So remember, the gradient of f is lambda times the gradient of g. So why don't we take a look at this equation first, because the components have to be the same. So I have 2x is lambda times 2x. All right, well, let's see. I can divide both sides by 2. There's no problem with that. And then I'm going to subtract everything over. So I have 1 minus lambda times x is equal to 0. Now, there are two ways that this can come about, right? The first way that this can come about is if x is equal to 0, right? That would definitely satisfy this equation right here. All right, well, if x is equal to 0, remember that this needs to be true as well. So we have 0 plus y squared is 1. That means if our x is 0, y needs to be plus or minus 1. So we end up getting these 2 points. And if you remember the problem from last time here, these were 2 of the points that we had in our chart. All right, now what's the other situation here? The other way this equation can be true is if lambda is equal to 1. All right, well, so far we've used this part of the gradient and we've used this right here. Doesn't seem like we've done anything with the y's. So why don't we take a look at them? So we have negative 2y is 1 times 2y. Well, that's just negative 2y is 2y. And there's only one way that that can be true. It's if y is 0. So then once y is 0, once we know one of the x and y coordinates, we could plug it into the constraint to get the other one, because we need to be on the unit circle. So we have x squared plus 0 is equal to 1, meaning that x is plus or minus 1. So we have 1, 0, and negative 1, 0 that we get from that. Let's see, how did I get the lambda equal to 1 from here? Well, I have 2 things multiplying to be 0, right? So that means that one or both of those needs to be 0. And I explored the x being 0 over here, and I explored 1 minus lambda being 0, aka lambda being 1 right there. All right, now I have all 4 of these points. So I'm not quite done yet. Remember, we need to make our comparison. Let's make our little chart over here, have our little competition to see which one's the biggest, which one's the smallest. And let's see here. So if I plug 0, 1 into my original equation right here, let's see, what am I going to get? It looks like I'm going to get negative 2. If I plug 0, negative 1 into here, it looks like I'm going to get the same thing. All right, now I'm going to take 1, 0 and put it into here. I have 1 minus 0 minus 1, so that'll be 0. And then the same thing happens with negative 1, because I square it and get positive 1 right here. All right, so then that means that our absolute max for this problem happens here at one of these 2 points, and then the minimum happens here at one of those 2 points. So they're at the extreme ends of the circle here, all 4 corners of the circle. All right, so let's go ahead and find the maximum and min values of this on the disk here. Now, this becomes a bit more of a problem because we don't just have one constraint curve, we actually have a less than or equal to sign right here. So we're doing the same thing we did but last class, but easier. I don't know if it's always easier, but it's just a different way of doing it. This is, think of this as like lecture 17.2. This is like an alternative way of doing a lot of different max and min problems. And we're going to see the strengths and weaknesses of it. One weakness, though, is that it doesn't handle inequalities very well. So in order to do this, we have to use the second derivative test on, or sorry, not use the second derivative test. Find critical points on the interior. And then 2, either use Lagrange multipliers or substitution. And by substitution, I mean what we did in last class, where we substituted in the constraint equation. All right, so that's what we need to do if we have some kind of inequality and we want to do the whole disk. If we ever have a filled in kind of area, we need to find all the critical points on there, and those are automatically candidates. And then we can use either Lagrange multipliers or what we did last class on the boundary. So Lagrange multipliers is good at handling the boundary here. Okay, now here's another drawback, unfortunately. The method of Lagrange multipliers doesn't work well for constraint regions like the square or the triangle because there's not just one equation to represent those shapes. So it worked well for the circle because the unit circle just has a single equation right here. But if say you wanted to draw a unit square, like it went out to the points 1, 1, -1, -1, 1, -1, and -1, 1, there's not just one equation for that. You'd actually have to split it up into 4 different equations, one for each piece of the square here. So that is one warning. In that case, you're pretty much forced to do it in the way that we learned last class. All right. So let's try another one of these. Let's get more practice doing this, because it's a little bit strange at first. And there's not a really nice Calc 1 version of this either. So it's kind of hard to get an intuition. All right, so find the maximum and minimum values of x, y subject to x squared plus y squared minus xy is 9. All right, so we know that the gradient of f needs to be lambda times the gradient of g. And then we also know that x squared plus y squared minus xy has to be 9. So these are our equations right here. All right, so why do we learn the Lagrange method if it's more restrictive and inefficient of doing something? For the problems where you can use it, it can be a lot better. Like this problem, you might be able to do this using what we did last class. It's definitely going to be better using Lagrange multipliers. So it's kind of like, think of it as more like kind of a specialist method. Like for the problems that it works on, it works pretty well, but it's a little bit less general. All right. So anyways, let's go ahead and find our gradients here. So the gradient of f, let's see. So we have the x derivative of this, which will be y. And then we have the y derivative of this, which will be x. All right, meanwhile, this is supposed to equal lambda times the gradient of g, which will be 2x minus y, and then 2y minus x. All right, so that's what our Lagrange equation ends up being. So let's write this out a little bit. So we have y is lambda times 2x minus y. And then we have that x is lambda times 2y minus x. Okay, it seems like there's a fair bit of symmetry going on here. It seems like these are just the same thing, only where I flipped x and y right here. So what I'm going to do is I'm going to try to set these equal to each other. What I'm going to do is I'm going to multiply the top equation by x, and I'm going to multiply the bottom equation by y. And now notice that they're now both equal to each other because we have both an x and a y in their product here. So now we know that lambda x times 2x minus y has got to be lambda y times 2y minus x here. All righty. So what we can do now is we can go ahead and cancel out our lambdas. All right, and then we can multiply through here. Like that. How can you do this multiplication without accidentally adding a solution that we wouldn't have originally had? Yeah, multiplying by x and y. Well, 0, 0, we don't need to worry about that as a solution because 0, 0 doesn't actually satisfy the constraint for this. So that would be a concern maybe if all this stuff were equal to 0, but in this case, we don't really have that going on. Could we have substituted y equals lambda 2x minus y into the other equation? Yes, we could have done it that way. I actually did it that way on paper earlier when I was preparing for this lecture, and that way is not fun. So I would definitely try to do it this way. If you could see some kind of way to, maybe exploit symmetry or something like that, I definitely recommend to do it that way. Yeah. Yeah, so I'm assuming here that lambda is not 0, and we'll talk about that in a minute. All right, so now we have 2x squared equals 2y squared. because we can cancel these guys out. So that gives us x squared equals y squared, or the x is going to be plus or minus y. All right. So let's see here. Let's take each of these situations separately. All right. So we have x equal to y. Let's do that one first. Now, once we get something like this, then we use the constraint equation because we used our gradient to get all of this, but we haven't used our constraint yet. So if x is equal to y, then every time I see a y, I'm going to replace it with an x. So I have x squared plus x squared minus x squared is 9. And where am I getting all of this from? I'm getting it from up here with my constraint. So remember, you need to use all of your equations if possible. So if you've already used the gradient to say get something like this, then try to use the constraint, or vice versa. All right. So we multiplied by x and y to set them equal. Yeah, that was the motivation here. We could have done this by substitution. We would have ended up getting the same thing, but it would have ended up taking a decent bit longer. All right. So anyways, back to this. We have those canceling out. And then we get x squared equal to 9, meaning that x has got to be plus or minus 3. So that means our critical points, or sorry, our points that we're checking will be 3, 3, and negative 3, negative 3. All right, now let's do this the other way, where we have x is negative y. All right. So let's see here. Why not set x equal to y? I mean, you could do it either way you want. I'm just substituting this into the constraint equation up here. That's all I'm doing for this, and that's going to give me what my x and y have to be specifically. Is that what you're asking about, or are you talking about something else? Are you still talking about this? Okay, well, anyways, yeah, we'll come back to that later if there are any questions here. Yeah, so the one thing about, so this is a system of nonlinear equations, and oftentimes those are kind of weird to solve, and you can solve them in many different ways. So if you're able to, as long as you're able to get this in some way, then it's okay how you want to do it. So you could do this by solving the original equations we had for y, and then substituting in here, and then using the constraint. That's totally fine. You could have done it this way. That's also fine. There's plenty of different ways to do it. The only difference between them is that some are quicker than others. All right, so let's go ahead and finish this off here. So if I see an x squared, that's going to be negative y squared, or just y squared. And then I have plus y squared from up here. And then I have minus x times y. Well, let's see, a negative x is y. So that's actually going to be another plus y squared. All right, so then we end up getting 3 of these y squareds together equal to 9. So then we have y squared is 3, meaning that y has got to be plus or minus the square root of 3. All right, and if I have a y value of root 3, then according to this, I need to have an x value of negative root 3. Oops, don't need a parenthesis. And vice versa. Okay, so these are going to be our points here that we want. Let's see here. So let's make a little chart. All right. Let's put these down. How do you know how many x and y coordinates you should have? It's different for every problem. There's not really a set number every time. So you can't really tell in advance. That's the thing about nonlinear equations. They're kind of messy. Okay. So let's see here. So when we plug these in, sorry, I got distracted for a second. All right, I'm back in focus here. So when we plug these back into our f, which was just x times y, we get 9 here, we get 9 here, we get negative root 3 times root 3 is negative 3, and then we get the same thing here. So these are going to be our maximums. And it's a coincidence that we keep getting 2 sets of 2. I know we had that in the previous problem. That's entirely a coincidence. You could just get 1. They could all be tied. Anything is possible. So these guys will be the maxes, and then these will be the mins. Now earlier, I kind of just flagrantly dismissed this lambda equals y, or sorry, lambda is equal to 0 possibility. What happens if we do that? So if lambda is equal to 0, then we have the equation y equals 0 and x equals 0. Reason being is that lambda would be 0, so both of these would, oh, sorry, let me move down. So both of these would be 0 right here, meaning that y and x would have to be 0. But 0, 0, as we said earlier, when we multiplied by these guys, that doesn't solve the constraint right here. Maybe it would be another story if we had like a 0 right here, but since this needs to be 9, we can't have both x and y being 0. So that's why I ignored it in this case. But it is good that you were thinking about that, because sometimes that can be relevant. All right. So why did I make it y squared instead of plugging in negative y? I did plug in negative y and I squared it. So the negative got squared away as well. All right. Let's do this again here. Get some more practice. How will we differentiate local mins or maxes with absolute mins or maxes? Yeah, sorry, I should have specified that earlier. All of these are absolute mins and maxes relative to the constraint. So if you decide to change what your constraint is, then these max and mins could be totally different. But as long as we stick with our constraint, these are the absolute biggest values you can find there and the absolute smallest values you can find there. So I think someone mentioned a restricted domain earlier. That is a good way of thinking about it in this case, whether it's between absolute and local maxes. All right, so let's go ahead and try another one of these. Find the max and min values for f of x, y, and z this time is x plus 3y minus z, subject to the constraint that we're on a sphere of radius 2. All right, so this will be our g of x, y, and z right here. All right, and the constraint is limiting the domain. Yeah, that's a good way of thinking about it. Yeah, the constraint sort of is your domain, because you need to satisfy this constraint equation to even be considered. That's why we kind of ignored this solution right here. All right, now the only difference between this problem and the previous problems is there's just one more variable. And all that means is we're just going to get one more equation in our gradient. So we have that the gradient of f is lambda times the gradient of g, and we have our sphere. All right. So let's see, what's the gradient of f this time? We actually got a pretty nice gradient this time. So the x derivative will be 1, the y derivative will be 3, and then the z derivative will be -1. All right, and then what about the gradient of g? Well, let's see, we're gonna get 2x, 2y, and 2z from that. Okay, so this gives us a few equations right away. We see that 1 is 2 lambda x, 3 is 2 lambda y, and -1 is 2 lambda z. Okay, so we can immediately solve all of these equations for x, y, and z by simply dividing by 2 lambda. So x is 1 over 2 lambda, y is 3 over 2 lambda, and z is going to be negative 1 over 2 lambda. Okay, so we used our gradient to tell us that. And now what we're going to do is we're going to take all of these, put it into here, and that should let us know what lambda value we're going to end up having. So let's see, x squared will be 1 over 4 lambda squared. Y squared will be 9 over 4 lambda squared. And z squared will be 1 over 4 lambda squared. And all of that has to be 4. All right, so I'm going to clear the denominators here. I'm going to multiply everything by 4 lambda squared. So I have 1 plus 9 plus 1 is 16 lambda squared. So this gives me 11/16 is lambda squared, meaning lambda needs to be plus or minus the square root of 11 over 4. Very interesting number. Okay, so we have our possible lambda values here. Where did the 4 lambda squared come from? We squared 2 lambda. All right, so now that we have this, then we're simply going to be able to get, our x, y, and z very easily, because we know that how x depends on lambda, y depends on lambda, and z depends on lambda. So if we take the positive root here, and this will almost always happen for these problems, you'll have some kind of split situation where you need to consider things one way and then consider things a different way. So x is going to be 1 over 2 times this. So I think that will simplify to 2 over root 11. All right, y, let's see here. If I plug root 11 over 4 into here, I think that will give me 6 over root 11, if I'm not mistaken. And then if I plug root 11 over 4 into here, I get negative 2 over root 11. Okay, so there's one point. And then my other point over here, where I take the negative value, it'll actually just be the negatives of all these. There we go. So these are our 2 points. And then they meet to have a little face-off to see which one is the biggest one and which one is the smallest. Okay, so we have 2 over root 11, 6 over root 11, and negative 2 over root 11. So if we stick this into our original equation, which way back here was this plane, or, well, it's not quite a plane because we have 4 variables now, but this linear equation at least, it's going to be 2 times 1. So we have 2 over root 11. Then we have 6 times 3, which will be 18. So then we have 20 over root 11 total. And then we subtract negative 2 over root 11. So that gives us 22 over root 11. Let's see. And that could be simplified to 2 times root 11 right here. And then I bet you could guess what's going to happen without even doing anything for the other point. What do you guys think this one's going to be? Without even like really calculating it. Yeah, that's right. It's just going to be the negative version. Okay, so then this one is going to be our minimum, absolute min if you want to label it. And this one will be our absolute max. There we go. Yeah, so the annoying thing about Lagrange multipliers is that the procedure for solving a nonlinear system of equations really depends on what kind of equations you have. So there's not really like one way to solve all of these guys. And in fact, what may happen is there may be multiple ways, but unfortunately some may take longer than others. So the best way to do these is to just try something. Just try the first thing you think of and just hope that it'll be something that's viable here. Why did we do this differently for the previous problem? By solving x and y? Well, that's exactly which is what I was saying. So it's it really just depends on the problem. Like each one of these is going to be different. Okay. Now let's see here. So we're supposed to do Lagrange multipliers with two constraint equations if time permits. And does time permit? Yeah, time permits. We have 15 minutes. So let's go ahead and try this out. So if we have two equations, then the gradient of f will end up being lambda times the gradient of g plus another multiplier called mu times the gradient of h, where both of these are constraints. All right, so we have multiple Lagrange multipliers here. All right, so let's see how this pans out here. So find the minimum distance from the origin to the line of intersection of the two planes, this right here and then this right here. This I'm going to refer to as G. And then this I'm going to refer to as H. Okay, now this is G and this is H. Then what do you think we're going to be using for our F? What are we trying to find an extrema of? Well, we're trying to find the minimum distance, right? So this distance is from the origin to somewhere else. So that means our equation will be root x squared plus y squared plus z squared. So this will be our f of x, y, z. Or it would be if we didn't know this really convenient trick to do when we are dealing with distances. So if you ever want to maximize or minimize a distance, don't actually use the real distance, use the distance squared instead. So we're not going to do this. We're really going to try to minimize the distance squared. Okay, and then why can we just get away with doing that? Why can we just get rid of that square root right there? Well, think about it. If you're trying to minimize the thing that you're putting under a square root, how do you do that? Or sorry, if you're trying to minimize a square root, I just gave my answer away. You minimize the size of the thing that's inside the square root. If you want to make a square root as large as possible, you just maximize the size of the thing inside the square root. So we could just focus on what's inside the square root if we ever have an optimization problem with that. Let's see. All right, so this is going to be our f of x, y, z. All right, so let's write down our equations. So the gradient of f, well, let's see, that won't be too bad. It'll be 2x, 2y, and 2z. And then we have lambda times the gradient of g, which is 1, 1, 1. Okay, and then, oops, that's not an equal, it's plus. And then we have mu. Oh, say it asks for maximum distance. How would you change your D formula? Well, that's kind of a degenerate problem, because if you want the maximum distance, then that would just be infinity, because you could just travel along the line as far as you can, and it would just go on forever. So that doesn't really have like a nice solution here. All right. Oh, is the mic bad? Is the mic bad? All right, well, let's just turn it off and on. All right, is that better, guys? All right, wonderful. All right, so then let's go ahead and do the gradient of h. That'll be 2, -1, 3. So at least these were pretty easy to do the gradient of. All right, and then we have our constraint equations. X plus y plus z is 8. And then we have 2x minus y plus 3z is 28. All righty then. So let's go ahead and write these equations out from the gradient here. All right, so we have the 2x is lambda plus 2 mu. 2y is lambda minus mu. And 2z is going to be lambda plus 3 mu. Now, what we can do is divide by 2 in all of these situations and get that x is 1/2 lambda plus mu, y is 1/2 lambda minus 1/2 mu, and z is 1/2 lambda plus 3/2 mu here. Okay, now what do you guys think I'm going to do with this information? Now that I have X, Y, and Z written in terms of the Lagrange variables, what am I going to do here? Now we're not going to suffer. This one's not too bad. Well, we got these from the gradient of F, so we've already used information about F, but what haven't we used? That's right. We're going to plug it into the constraints here. So what I'm going to do is I'm going to take these and I'm going to put it into this. So I have 1/2 lambda plus 1/2 mu. So that's my X. And then I have 1/2 lambda minus 1/2 mu. That's my Y. And then I have 1/2 lambda plus 3/2 mu. That's Z. And then we have 8. So if I combine all of these, those will cancel out. And I think I get 3/2 for both of them. Yeah, so I have 3/2 lambda plus mu is 8. All right, so that's what we get from our equation there. And then X is just plus mu. What? Oh, yeah, it is. Oh, someone's saying something else. Okay. Wait, the first mu is not 1/2. Oh, yeah, okay. Something felt a little off about that. Yeah, okay, so then this is not right. This is going to be, it'll still be 3/2 lambda, but it should be 2 mu instead. There we go. And if I multiply by 2, I have 3 lambda plus 4 mu is 16. Okay, there we are. You're out of room. Well, fortunately, Dr. Huang was kind enough to provide us with an entire blank sheet of paper for this one. So don't worry, we got enough room here. All right, so then let's go ahead and plug these into the other constraint here. So we have 2 times X, so that'll be lambda plus 2 mu. Then we have minus Y, which will be minus 1/2 lambda plus 1/2 mu. And then we have 3 times Z. So it'll be 3/2 lambda plus 9/2 mu. And all of that needs to add to be 28 right here. All right, let's see if I can add this up correctly this time. So I have lambda minus 1/2 lambda is 3/2 lambda plus 3/2 lambda will just be 3 lambda. All right, and then I have 2 mu plus 1/2 mu, so that's 5/2 mu, plus 9/2 mu would be 14/2 or 7 mu. It's 28. Okay, so this is my second equation for lambda and mu. All right, now let's see here. Here's the other one that I got earlier.
Professor Manley, I think it's supposed to be 2 lambda.
You're right. Wait. 2.
For the one you just solved, because it's lambda minus 1/2 lambda would give you 1/2, and then plus 3/2 would give you 2.
Oh, you're right. You're right. You're right. Thank you very much. Is that right, though? Let's see. Oh, my God. So many variables. Let's see. Okay, well, let's just go with this for now. Well, I don't think this, I think we made a mistake somewhere. Let's see. So these were definitely right back here. Okay, I take X, multiply it by 2. I get that. Okay. I take Y and I subtract it. Get this. Take Z, multiply it by 3 and get this. Okay, so I do get 2 lambda. And then 5/2, 9/2. Oh, no, that's right. That's right. Okay. Okay, everyone's just saying lambda now. All right. Anyways, let's try to finish this off here. So what I'm going to do is I'm going to solve. I'm going to solve this one for lambda and then substitute it in here. So I have 3 lambda plus or 3 lambda is 16 minus 4 mu. Lambda is 16 thirds minus 4 thirds 4 thirds mu, like that. And then we can put that into here. So then we have 2 lambda, which will be 32 over 3 minus 8 thirds lambda plus 7, oh, sorry, mu, yeah. Plus 7 mu is 28. All right. It's getting a little hairy here. Let's see. 32 over 3. And then we have this right here. It's 2. You're saying this is 2? Was this supposed to be 2 right here?
It's 3 plus 2 mu equals 16, I think.
Oh, 3 plus 2 mu is 16. Okay. Wow.
Oh, I think it was right before, because it was 3 halves mu, or 3 halves lambda, and then you just multiplied everything by 2.
Yeah, that was right. 3 lambda plus 4 mu. Yeah, okay. And then I think everything's good so far. I remember getting the answer mu is 4 and lambda is 0 earlier, which works with 3 lambda here. And then, well, it actually works with no matter what lambda is. I don't know. It's Friday. I'm getting a little lost. Let's see. So what were we doing here? Let's see. So we have 13 mu over 3 is 28 right here. Okay, you know what? Going through all this algebra is not really doing anything for us. I want to explain the process of this, and I'll mess up algebra on someone else's time. So what we're trying to do here is we found the gradient of our constraints. So we found those ended up being pretty simple here. And then we set x, y, and z equal to these right here. We had 2x is lambda and 2 mu, 2y is lambda and negative mu, and 2z is lambda plus 3 mu right here. I divide everything by 2 to get this, and then I substituted these 3 into my equations right here. All right, so there we go. So I did that, and then that's when all this insanity happened with the algebra, because I have 2 of these for each variable here. So we ended up having 6 of these for each. And if I'm not mistaken, the answer does end up being mu is 4, lambda is 0 for this, because 7 times 4 will be 28, and then we don't have any lambda. And then 4 times 4 will be 16, and then we don't have any lambda. So I'm pretty confident that, algebra aside, I think we end up getting this. So I'll save some time with that. And then we can go ahead and substitute these back into x, y, and z. So x will be 4, y will be negative 2, and z will be 6. So this is and remember what we were trying to solve for originally, this is the point on the line of intersection closest to the origin. All right, so if we managed to muddle through this algebra probably a little bit more, we wouldn't end up with this result right here. All right, so time is not permitting us to do any more now. So I will see you guys on Monday, where we will be doing something totally different, meaning we're going to start integration with multiple variables. So I will see you guys on Monday. Sorry about messing up.
Could you possibly just scroll up a little bit to see what the question